squared. That's kind of the give me part of the problem. That part is always the bottom squared. All right, you want to start going through? So you have to take derivative of this first, right? So what do you see there? Composite, right? So you're going to use chain. So go ahead.
5 plus 4
Good. To the fourth.
times 3x to the power minus 2.
Okay, sorry. What did I do? What did you do? So you did the 5 out, this to the fourth. Got it, right? But you said it was composite, right? So you still need to go inside and take derivative of that part, which was 3x squared. I thought that's what you were saying, but then you said to the fourth, and I was like, whoa, wait a minute, hold on, she's giving me this, right? So that's the derivative of the top, right? Now you say times the bottom. Yeah? So when I do that, do I need the bottom in parentheses? What do you think? How many terms do you see? 2, so we need to put it, right? Okay, everyone following up? We're not done, right? That's just f prime g. Now, minus, you're going to do this one, right? We now need to take the derivative of this one, right? So
3 times 4x cubed.
12, so 12x cubed. That's the derivative of the bottom, right? And then derivative of that's 0, so we don't need it. So that's the derivative of the bottom, and then just times the top, right? And that's it. We're done. We're done with the raw derivative. So again, if this is f up here and this is g, then this piece right here is f prime. Sorry, it's messy. This is g minus this, just right here. That's g prime, and then this right here is f, and then this whole thing here is our g squared. Yes?
My answer still be considered right. I did the same thing, but on the formula over here, it's g of x first instead of f of x.
Yeah. That would be correct if you followed that formula,
Okay.
right? But that's not the way I taught it, only because, what did I tell y'all? It's easier to memorize if you do it the way that I taught it in class, because it's really only like one formula you have to memorize. But if you're going to go off the sheet, you're not going to get it wrong. It's just going to look different.
Yeah, it's just equal to the same thing.
Yeah, you get the same thing, though.
Okay.
All right? Okay, good. Let's see. We got 5 more minutes. Ooh, that's interesting. What I think I've noticed about this worksheet is that it doesn't have any trig functions. That's the drawback to it. It doesn't have chain rule with any trig stuff. It's all algebraic stuff. I think I'm going to ask for a volunteer on this one, but nobody who's already answered today. All right. Do I have a volunteer? Go ahead. So tell me what you're seeing. Let's walk through this together. What do you see?
So originally chain rule.
Chain rule,
Yeah.
okay. And what is the outer layer of your chain?
It's going to be all of the inside.
Yep.
with power.
To the fourth power, right? So I get to use my backpack, right? Got my backpack to the fourth power. So derivative of that should be, go ahead,
It's going to be
4. And then
the entire argument
the entire argument, it'll wind up being to what power?
to the third.
To the third. So we're just going to take that 4 out front. We're going to rewrite all of this to the third power. Now all of that is just x plus 5 to the 5th minus 1. Okay. Continue.
And we're going to do the derivative of our argument, but it's also a addition and subtraction problem.
Okay.
With a chain rule in it.
Okay.
So it's a good combo. So then you're going to take the derivative of x plus 5 to the 5th.
Okay.
As a chain rule.
Okay.
So it's going to be 5.
I'm going to put, so let me rephrase. You're doing it right, but let me just, we're now looking at the inside, right? And when I look at the inside, I see this minus that, right? When I take a derivative and I have subtraction, I can do this and then subtract the derivative of this, right? What's the derivative of this going to be? 0. So I don't really care about this now, right? Because I'm about to take derivative of this, that's going to go away. So all I really care about is derivative of this, which is
It's going to be 5.
5. So you're doing chain again, right?
And then this is x plus 5.
X plus 5, you're not touching that, and it's to the 4th.
And then the derivative of the inside should be 1.
And then times the derivative of what's in here, which turns out to just be 1, because you can do these separately, right? And you just get derivative of x is 1. Now, we don't need to write the 1, do we? But I'm going to put it here just so we understand we did do the chain rule, right? Anybody have a question there? Yes? Why is it a 1 back here? Okay, so when we're doing derivative of this, first thing comes, the 5 comes down, right? And then it's all of that to the 4th, right? Then what we're supposed to do is take derivative of what's in here, right? What's derivative of that? What's the derivative of x? 1. What's derivative of 5? 0. So 1 plus 0 would be 1. I'm just putting it there because I want you to remember, we did do chain rule here, right? We did do the derivative of this. We didn't forget about it. It just turned out to be a 1. Had this been 3x, let's say, right? Then what would have been here? A 3, right? It wouldn't have been a 1. So we want to make sure we're paying attention to that. All right, let's try and squeeze one more in here. I went in, I searched just now for chain rule with trig functions. And I was able to find some stuff here. And yeah, this is a good one. I'm going to send you all this as well. Let's get right into the frying pan here. Which one do y'all want, 7 or 8? Do 8? All right, let's do 8. Let's do them both. Let's do them both. I think I'm going to walk through these, all right? Just because time. On this one right here, you need to be clear on the notation and what it means. This cubed means I'm cubing the sine function. This 5th power is only acting on the x. So this really looks like this. Sine, the argument inside of that is x to the 5th, but then all of that is being cubed. That is what that notation means. Do y'all see that from that notation, that that's what it represents? This cubed is what's acting on the entire sine, and then the 5th power is only acting on this x. Look at that compared to this one. What this one is, that 2 right there, that 2 is only acting on the argument in here. This squared is not squaring the entire cosine. If I wanted to square the entire cosine, I wouldn't put a 2 here, I would put it here. Do you see the contrast, those two notations? Okay, let's take a derivative. On this one, does anyone want to tell me? When you start to get good at chain rule, you can just kind of like verbally just start saying it. Anybody? Go ahead. Go.
First
3 parentheses. X to the 5th, okay. to the second power. Perfect. That's the outer layer, right? That's the outer layer of the onion that we have the third power. So we bring it out, all of that squared. Okay, times, keep going. So we've done this, right? So now we're just looking at this. When we derivative of this, you're saying it's cosine of what? Cosine. Cosine of x to the fifth. So you're only doing the sine part, you're leaving the argument alone, and now you're moving into the next layer, so times 5x to the fourth. Perfect. That's it. 3 layers to that onion. Outer layer was the cubed, the middle layer was the sine, the inner layer was the x to the fifth. So you just kind of chip your way. Yes?
I'm just kind of confused how you got, how like you kind of reformatted it into that, with the parentheses and stuff, because if I were to see that like...
Oh, like to reformat it this way?
That.
Well, I'm doing that because if you're not sure how to reformat that, now I'm showing you that's the way it would be. Okay. If you're unfamiliar with that, I figured a lot of you would be like confused, what does that mean? So I wanted to show you exactly what this means. It means this. Okay. So if you have this, if you have, let's say, sine, and you have some power here, like, let me use something else, 4, like that, of x. This means you're taking that sine function and you're raising it to the 4th power. That's what it means. But you have to be careful because, you know, look at that versus this, sine of x to the 4th. If I write that, that's not the same thing. What this means is that you're taking sine and inside you're plugging in x to the 4th. See here the 4th power acts on x. Yeah. So like for example, if I said, hey, plug a number into this, plug 1 into, or let's say plug 2 into this. If you plug 2 into this, what you need to do first is take 2 and raise it to the 4th power. Figure out what that is, and then take sine of that number. Understand? Mm-hmm. But over here, if I say, hey, plug 2 into this, you plug 2 in, you take sine of 2, take that answer and raise it to the 4th power. See, there's a difference there.
Yeah, it's just like a series of stuff.
Yeah, so notation there is important for us to understand what these two things represent. Okay, who wants this one? Anyone? Anyone? Bueller? I'm going to call on somebody. Boom, boom, 15. Ooh. So last person was Sophia, was 19. 18, 17. It's Dalton. You feel okay with this one? Yes. Okay. All right, so what do you see here, Dalton? Do you see chain, product?
Chain and then another chain.
Good. All right, so let's start with the outer layer. What's the outer layer here for us?
That would be the cosine.
Cosine. Okay, so what do we do? What's the derivative of cosine?
Negative sine.
Negative sine, perfect.
Negative 3x squared plus 2 to the power 2.
Perfect. See, we didn't touch the argument. We just did the outer layer first. Good job. Times, you want to keep going?
Yes.
Be
Times 2 times negative 3x squared plus 2 to the power 1.
Okay, I'm going to put the 1 there. We don't need it, but I'm going to put it there.
And then times negative 6x.
Perfect. That's it. Everyone see that? Good job. So derivative of the outer function, don't touch the inside. Now, once we've done cosine, we've got this squared, right? So we're going to bring the 2 out, this to the first power. Boom. Now we've done the 2. Now we take the derivative of that, and that's this, and we're done. Okay. I haven't looked at this whole worksheet, but I'm going to send this to you all as well. Sound okay? Why is that not doing that? There we go. And those also have answers. What did I tell you all about chain rule? About how important it is? So if you can't do chain, right, your calculus life is over. And that's just the truth, all right? I'm not trying to scare you or, man, he's so negative. No, I'm just being truthful, all right? You have to be able to do chain. If you can't do chain, you can't do calculus. I remember when I was when I was a student trying to get my shit together at some point, I remember I was about to take calculus. I had just taken pre-cal, and I was going to be a good student, and I was going to try and prepare for calculus before I took the class. So I picked up the Cliff Notes. The Cliff Notes, you know what those are? It's like if you don't want to read To Kill a Mockingbird, you buy the Cliff Notes, and it kind of gives you a summary of what the book's about, right? So I got the Cliff Notes for calculus, and I can remember that it had something like this. It wrote like f of x equals sine of 4x, and then on the next line it had this, or well, it had a 4 in front. It had that, you know? And I had no idea what the chain rule was. I had no idea, you know, I was just like, what's calculus about? And I see this, and I'm like, how are they turning this into this? I couldn't figure out, like, what algebra are they doing, right? How does a sign become, I thought there was some identity or something. I was trying to figure out how to turn it, because I didn't understand what the chain rule was, because I was just trying to read the Cliff Notes. So it really, I was like, how, this is going to be like mysterious. I didn't know. So we have to formally go through the process of learning it, right? Learning all the rules, getting comfortable with them. And then, as soon as we get comfortable with them, we're going to start to throw a curveball to you. So that's now what the rest of class is about, all right? So the next section, let me try and motivate this idea with some pictures first, all right? Before I even tell you what this section is about. Let's say we take this function, f of x equals x squared, all right? I'm going to graph this for you. I'm going to graph it. I'll graph it in black, or in blue. All right. It's just a parabola, right? Now, if I go to, let's say, x equals 1, I go up to this point. That point is also 1, right? Plug in 1. 1 squared is 1. Now, if I wanted to know what the slope of the tangent line is there, then what I would do is what? If I asked you for the slope of that red line, what would you do? It's rise over run, but where are you going to get it from? I mean, what in this class allows us to find slopes of tangent lines? The derivative, right? That's what the derivative is, right? The derivative gives you the slope of the tangent line. So if I wanted to know the slope of that, then all I would do is take the derivative of this function. What's the derivative of that function? 2x. And then, to figure out the slope right there, I would go to this x value, right? X is 1. And I'd plug it in right there. So if I want to know the derivative at 1, I get 2 times 1, which is 2. So that is the slope of the line, right? That's the fundamental idea here, right? You have a function, you graph it, you want to find the tangent line. All you have to do is take the derivative and then go to whatever x value and plug in, you can get the slope of the tangent line. So what if I went to the value 2 here? Went up here, what's the slope of the tangent line there? What is it? 4. How are you getting that? Taking the 2, plugging in here, 2 times 2 is 4. Right? If I go out to 3, up, slope of tangent line there would be 6, right? All right, that's what we've been doing. Now I'm going to graph something else for you. It's a circle, right? And then what I'm going to do is I'm going to go to some value of x. I don't know, I'm just going to pick a value here, right here. Some value of x, I don't know what it is. And then I'm going to go up to this point right here. Do you all agree that there's a tangent line for that point? something like this. And I should be able to find the slope of it, yeah? But do you also agree that for the same x-coordinate, there's also a point down here, and that point has a different slope? At that point, we have a different slope, yes? And if I do that for any x value, right? If I pick another x value over here, go up, I have a point here, I have a certain slope there. If I go down, I have a certain slope here, right? Where over here in this picture, if I gave you an x, right? If I gave you an x, there was only one point. And that means there was only one slope, right? But with a picture like that, for 1x, we have two different points. And that's because a circle is not a what? A function. A circle is not a function, right? What do functions have to pass in order to be functions? Or what do, sorry, let me take that back. What do curves have to pass in order to be characterized as functions? The vertical line test. So this passes the vertical line test, right? Any vertical line only hits it one time. So that is a function. This is not a function. So, you know, we've been studying functions, right? This is not a function. Sorry, that is not a function. We can find slopes of tangent lines for functions, you know, because we just take the derivative. But this does have tangent lines, right? I mean, we should be able to find those somehow. So this next section is about, can we take care of this case too? Do we have to have the requirement of being a function, or can we just have a curve and still be able to find tangent lines? So let me give you the equation of this circle. Okay, now I didn't give it a radius, but let's say it has a radius of 2. All right, that's the radius of this circle. Then here's the equation of that circle. X squared plus y squared equals 4. So I'm expecting, and especially from my pre-cal students, I'm expecting you all to remember this formula from pre-cal, that this is the generic equation of a circle that has a center. Your center is the point HK, and your radius is R. So if you replace this right here with the radius, replace H and K with whatever point the center of the circle is, that will give you the equation of the circle. So for us, the center of this circle is what? What does it look like? 0, 0? So if you plug in 0 for H, 0 for K, and plug in 2 for R, you get that equation right there, right? You'll see that? Yes? Okay. So I said here that this is not a function. You all agreed with me that this is not a function. Let's verify that this is not a function algebraically. If I said to take this equation and solve for y, try and get y isolated by itself. Let's do that. First thing I would do is subtract x squared on both sides, right? Subtract x squared on both sides. That would isolate the y squared. So all I did here was move this over. And now to get y, I would have to take the square root on both sides. But when I do that, what do you have to do every time you take the square root on both sides of an equation? What do you have to include? Plus or minus, right? Yeah, plus or minus. And now this is no longer a function. Why is this no longer a function? Because for a function, you should have one input and one output. You should never have one input and two outputs. But if you look at this, if I plug in, let's say I plug 0 into this, right? For x. What would you get? If I plug in 0, so 0 goes in, right? This is x, 0 goes in, what comes out for y? Well, you get 4. Square root of 4 is 2, but you have plus or minus 2, right? So what it comes out is actually two things, 2 and negative 2. And therefore, it fails to be a function, right? And you can see it. If your x value is 0, you have the 2 up here and the 2 down here, right? The two y coordinates, right? So it fails to be a function. So this section is about, can we find the derivatives, the slopes of the tangent lines on curves, even if they cannot be solved for y like this? Is it possible? And the answer is, of course, yes, right? And it requires a new kind of approach on the way we take derivatives. All right? So I'm going to bring up the formal notes for this, and we're just going to kind of skim through these. That was just kind of to motivate the idea. This section 2.6, right? 2.6 after chain rule is called implicit differentiation. Implicit differentiation. The word implicit comes from the word imply. So to imply something is to kind of express something without directly expressing it, right? Like if I say, you know, I love cars, then that's explicit. I'm telling you, right? But if you open up my book bag and you see a bunch of magazines about cars, that would imply that I probably like cars, right? I haven't stated it. So there's a difference between explicitly saying something and implicitly stating something. So let's look at the difference between explicit and implicit equations. Everything you've studied in your life up to this point has been an explicit equation. Okay, I'm not going to go through all this. I'm just going to show you. Okay, these are explicit equations. This is missing the square root, and I don't know why. Look at all those equations. What they have in common is that they all involve, these are three different equations, right? They all involve two variables, x and y. And in each one of these, notice that you have one of the variables isolated. So here, y can be determined. If you give me x, I give you y, right? You give me x, I'm going to know what y is. So y, it's explicitly known. As long as you know x, you're going to know y. Here, same thing. Give me x, I'll take sine, I'll take square root, that'll give me an answer. Here, it's a little reversed. If you give me y, I can give you x, right? So these are all explicit equations. And finding the derivatives of those is not a problem because it's what we've been doing, all right? Now some implicit equations. That right there. That's a circle, right? I just did the one x squared plus y squared is 4. That's a circle though with a radius of, this has a radius of 4. If you try and solve for y, what happens? You get the plus or minus, right? So you don't have it explicit because there's two different outputs. Even if you try and solve this for x, you can't. This one right here, if you try and solve for y, you'll never be able to, all right? There's no way you'll ever, no algebra that you know, that you'll ever be able to get y by itself. So trust me on that, you can't. And x, if you try and get x, it won't work. And then same with this one. You cannot get x or y isolated on one side of the equation. All of those are examples of implicit equations. So let's look at those graphs. Where is it? I think I have those graphs ready to go. No? Yeah. Okay, so there was that first equation. This was, what you're looking at there was x squared plus y squared is 16. Circle of a radius 4, centered at the origin. What I want you to see there, it fails the vertical line test, right? But at every point, we should have a tangent line, right? So we should be able to figure out a way to do that. Let's look at the next equation. And that one is this equation right here. X cubed plus cosine y equals x plus y squared. Ready to see that graph? Huh. Kind of weird looking graph, isn't it? Does it pass the vertical line test? No, right? But does it make sense that we should be able to find tangent lines on there? Hold on, where's my slider? There it is. No? Do y'all see my slider anywhere? I guess I didn't make a slider. Okay. Well, do you agree that right there at that point I have a tangent line? But for that same x value, there's a point below it, right? There's a point there. And there, for that same x value, there's a point up here and a point down here, and they both have tangent lines. And they're different, right? They're different answers. They're different slopes to those two lines. So can we find the slopes of those? That's what we want to be able to do. And then the last one, this equation right here. You ready to see that one? Wow. Okay. All right. That's what it looks like. Does this pass the vertical line test? Absolutely not, right? So if I go to some x value right now, right? If I go to some x value, let me see if I have this set up here. There's an x value, right? I pick an x value, and then there's a point right there, and there is a tangent line to that one, right? Definitely. But for that same x value, there's another point there, and that has a tangent line, doesn't it? And if I go to a different x value down here, same x value, there's another y value down there, and that has a tangent line, and that's where I stopped. But I could keep going, right? For this x coordinate, there's actually like an infinite number of points that correspond to that x value. I'm probably going to freak Desmos out. Desmos doesn't know what to do anymore. He gave up. Okay? There are an infinite number there. So the key takeaway from this idea is that, look, when we're dealing with these things that aren't functions, if we want to find the slope of the tangent line, knowing the x value is not going to be enough. We're actually going to need to know the x value and the y value so you know exactly where you are, and then you should be able to find the slope. All right? So here we go. The best way to learn implicit differentiation is by example. All right? I can sit here and try and tell you like theoretically what we're doing, like give you steps. But it's kind of like the chain rule. You got to see examples, and then you start to pick up on it. All right. So I want us to talk a little bit about notation. If I were to write, before we start this, if I were to write this down, what would you tell me that is? 2x, right? You would say 2x. Now, did you use the chain rule there? No? You used the power rule, right? The power rule, just 2 came out. That's the first